Okay, so now I'm going to show you the nonce-based version of CBC encryption. So in this mode, the IV is replaced by a non-random but unique nonce. For example, the numbers 1, 2, 3, 4, 5 could all be used as a nonce. And now the appeal of this mode is that if the recipient actually knows what the nonce is supposed to be, then there's no reason to include the nonce in the ciphertext. In which case, the ciphertext is exactly the same length as the plaintext. Unlike CBC with a random IV, where we had to expand the ciphertext to include the IV, here, if the nonce is already known to the recipient, there's no reason to include it in the ciphertext, and the ciphertext is exactly the same length as the plaintext. So it's perfectly fine to use a non-random but unique nonce. However, it's absolutely crucial to know that if you do this, there's one more step that you have to do before you use the nonce in the CBC chain. In particular, in this mode now we're going to be using two independent keys, K and K1. The key K is, as before, going to be used to encrypt the individual message blocks. However, this key K1 is going to be used to encrypt the non-random but unique nonce, so that the output is going to be a random IV, which is then used in the CBC chain. So this extra step here of encrypting the nonce with the key K1 is absolutely crucial. Without it, CBC mode encryption would not be secure. In particular, if you just directly use the nonce, feed that into CBC encryption, in other words, you use the nonce as the IV, then we already know that a non-random nonce would not be CPA secure. We saw that on the previous slide. But in fact, even if you set K to be equal to K1, in other words, you just encrypt the nonce using the key K, that also, is not going to be CPA secure and can lead to significant attacks. So I want to make sure you understand that if the nonce in CBC mode encryption is not random, this extra encryption step has to take place. And, so I'll make this extra step kind of dance here just to make sure you never forget to put it in. And I'll tell you that this is an extremely common mistake in practice. There are many real-world products and crypto libraries that actually forget to encrypt the non-random nonce before using it in the CBC chain, and that actually leads to a practical and significant attack. For example, this was not done in TLS. TLS, as we said, used predictable IVs, and that led to a significant attack on TLS. Moreover, the reason this is so important to know is that in fact many crypto APIs are set up to almost deliberately mislead the user into using CBC incorrectly. So let's look at how CBC is implemented inside of OpenSSL. So here are the arguments to the function. Basically, this is the plaintext. This is the place where the ciphertext will get written to. This is the length of the plaintext. This is the AES key. Finally, there's an argument here that says whether you're encrypting or decrypting. And the most important parameter that I wanted to point out here is the actual IV. And unfortunately, the user is asked to supply this IV, and the function uses the IV directly in the CBC encryption mechanism. It doesn't encrypt the IV before using it. And as a result, if you ever call this function using a non-random IV, the resulting encryption system won't be CPA secure. Okay, so it's very important to know that when calling functions like this CBC encryption in OpenSSL, either supply a truly random IV, or if you want the IV to be a counter, then you have to encrypt the counter using AES before you actually call CBC encrypt. And you have to do that yourself. So again, it's very important that the programmer knows that it needs to be done, otherwise the CBC encryption is insecure. One last technicality about CBC is what to do when the message is not a multiple of the block cipher block length. That is, what do we do if the last message block is shorter than the block length of AES, for example? So the last message block is less than 16 bytes. And the answer is that we add a pad to the last block so that it becomes as long as 16 bytes, as long as the AES block size. And this pad, of course, is going to be removed during encryption. So here's a typical pad. This is the pad that's used in TLS. Basically, if you pad with n bytes, then essentially what you do is you write the number n times. So for example, if you pad with 5 bytes, you pad with the string 55555. So 5 bytes where each byte is the value 5. And the cute thing about this pad is basically when the decryptor receives the message, what he does is he looks at the last byte of the last block. So suppose that value is 5, then he simply removes the last 5 bytes of the message. Now the question is, what do we do if in fact the message is a multiple of 16 bytes, so in fact no pad is needed? If we don't pad at all, then that's a problem, because the decryptor is going to look at the very last byte of the last block, which is now part of the actual message, and he's going to remove that many bytes from the plaintext. So that actually would be a problem. So the solution is, if in fact there is no pad that's needed, nevertheless we still have to add a dummy block. And since we add this dummy block, this would be a block that basically contains 16 bytes, each one containing the number 16. Okay, so we add essentially 16 dummy blocks. The decryptor, when he's decrypting, he looks at the last byte of the last block. He sees that the value is 16, therefore he removes the entire block, and whatever's left is the actual plaintext. So it's a bit unfortunate that in fact, if you're encrypting short messages with CBC, and the messages happen to be, say, 32 bytes, so they are a multiple of 16 bytes, then you have to add one more block and make all these ciphertexts be 48 bytes just to accommodate the CBC padding. I should mention that there's a variant of CBC called CBC with ciphertext stealing that actually avoids this problem, but I'm not going to describe that here. If you're interested, you can look that up online. Okay, so that's the end of our discussion of CBC, and in the next segment we'll see how to use counter mode to encrypt multiple messages using a single key.